because I just skip over them anyway. Or I talk through them really fast and nobody gets anything out of it anyhow. So, yeah, we're hopping up to page 90. I'll probably save a page on that. You know what I could do? I'll take this as a typo. I could take that page out and put it on my website as a tutorial page or an extra practice page. Save myself a paper page, but still have it available to folks. All right, so if anybody wants to submit that for a typo bonus, you're welcome to. You're the best. I have fun with this stuff. All right, so determinant. So it's either lambda I minus a, or, like I said, we could do a minus I lambda, or lambda I. All right, it really doesn't matter which way you go. Now, the dimensions of I should be consistent with the matrix that you're given. So this is a 2 by 2 matrix. So this is going to specifically be lambda I sub 2 minus a. All right. I sub 2 is the 1, 0, 0, 1 matrix. All right. So I'm looking at the determinant of, well, 1, 0, 0, 1 multiplied by lambda. So lambda 0, 0, lambda. Oh, nope, 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 undo. Now that's right, but we have to subtract from that a. And then find its determinant. All right. So we're looking at lambda minus -1, so lambda plus 1. 0 minus 4, so -4. 0 minus 6, -6. Lambda minus 9. That determinant needs to be equal to 0. So each one of these expressions should be parts of equations that are equal to 0. All right. So if we solve this characteristic equation, what we'll have is the set of eigenvalues, if they exist.
So it always has to be 2, 2, or 3, 3, 4, 4.
Yeah, it's got to be. They have to be square matrices. Yeah, you're not going to have an eigenvector that exists in a matrix that's not a square matrix. Good question. All right, so lambda plus 1 times lambda minus 9. We start off with the 2 by 2 because it's easy to find the determinant. Now you could also see how this is not really much of a calculator type question because, I mean, just look at it. All right, so minus diagonal up, so minus 24. Or at least it's seemingly not a calculator type question. You could still use the calculator to do the ordinary algebra stuff. I could solve this equation right now using my calculator. I mean, just x's instead of lambdas. All right? There's nothing wrong with that. In fact, I actively encourage it. All right? Because even though the course has algebra in the title, I don't want to do algebra if I can avoid it. Except when I'm teaching an algebra class, at which point I tell them, oh, I love doing algebra. I can do this all day long. And then I walk out of the algebra class, I'm like, oh, thank God that's over. So anyway, but I'll do it by hand, and then I'll go back and show you how you can do that on a calculator if you don't already know. So lambda squared minus 8 lambda, assuming my pen wants to function without turning off arbitrarily, minus 9 minus 24. All right, so lambda squared minus 8 lambda minus 33. $11 and 3. Lambda minus 11, lambda plus 3. And so lambda equals 11, and lambda equals -3. All right, is lambda equals -3 an eigenvalue? Yes. And the answer to y is C below.
How do you know in your head that it's 11 and -3?
Oh, well, I just looked at the factors of 33. The only way I was getting to a 33 was 11 and 3. And I just figured, how am I getting to a -8 from there? Like, if I'm going to get from an 11 and 3 to a -8, the 11 had to be negative with a positive 3. A little algebra 1 trick from back in the day might be helpful.
Yeah, I feel like I skipped it.
It's a good trick. And you know what? I'd use this trick all the time. You know, because sometimes like a 33 resonates with me, right? 35, that's another one. But sometimes you get to like 128 and you have like a bunch of different factors that can go into it. So this is coming from the operation of xy equals -33. So basically I'm looking for two numbers that multiply to equal -33. So xy equals -33. All right. So all I'm doing is solving this equation for y is equal to -33 over x. And so I'm popping that into the calculator and just looking at the table of values. And just looking at the ordered pairs to see which pair of values would add to give me a -8. All right, so nope, there it is. And so now I have my two factors. Okay, it's a little nifty algebra 1 trick that really goes a long way. There's another more complicated way of doing it that involves a stat editor. I don't know if it's necessarily worth it though.
What you did there, I get confused.
Say it again, sorry.
I get confused what you do.
Like how I did it? Yeah, so I typed in -33 over x. Then I'm going into the table, so second graph. Let me just get into the right neighborhood. I don't know why it knocked me off of my... And then I just start scrolling down the list to identify any pair of values that would add to give me the -8 that I'm looking for in the middle. All right. Now, I always forget what the prereqs are for certain courses, but I know you definitely had to take at least some level of calculus to get here. So there are other different, other strategies that you could use. One of them actually might be Newton's method. Honestly, I can't remember what programs I dumped into your calculators. Was it just the two? I gave you Pascal. Did I give you Pascal? Okay. So there was a program that I wrote called Newton's method that could be helpful also. But sometimes just having a simple quadratic formula program in your calculator can be useful. The problem with that is it only works for quadratics. So if we have something that involves solving a polynomial that's not degree 2, you'd be out of luck. So let me show you a technique that's already built into your calculator that's going to work regardless of the technique. So regardless of the function. So you type in the original equation. So, and this is before any algebra. All right, so I'm not even going to distribute. I'm not going to take the chance that I'm going to screw this up. So I'm going to type in x plus 1 in parentheses. So don't go looking for a lambda key. X minus 9 minus 24. I don't know why that keeps happening. You know what? I'm still in that program. It's like Nightmare on Elm Street. I'm still in the dream, or Inception for a more recent example. I mean, that's pretty disheartening. The fact that the guy never got out of the dream. Brutal. I'm just worried that it's going to happen again. I wonder if I should shut the app down. I'll just roll the dice. All right. So you put your function in, and then as a second equation, you put in y equals 0. All right? Because basically we're undoing the substitution technique for solving an equation. All right? So I'm just basically saying I have an equation y equals this and y equals 0. I want to find where they intersect. All right, there's two ways to do that. One is graphically, so I could take a look at the graph and see if there's an obvious intersection, and then use the functions that are built into the calculator to find that obvious intersection if it exists. All right, so now these are clean values, so I expect that if I just do a regular zoom on my calculator, it should be pretty obvious where those intersections are. All right, so we're looking for X-intercepts, and since they actually happen to be whole numbers, well, one's a whole number, one's an integer, you could actually just count tick marks on the screen and see where they are. But let's say you can't, let's say it's not obvious, or in the case of some of your calculators, yeah, the tick marks are not very trustworthy. Yeah, it looks like it's -3, but I'm not going to bet my life on it. So what we do is we hit second trace, and that brings us to the calculate menu, which I'm going to have to do on the other calculator. Right, so it's too different on this one. And there's no way for me to record this thing, so... Well, then I could show you another technique also after this. So this a little something for everybody in a minute. Let me just put this over here, line it up, narrate everything I do, because, you know, that's not weird. All right. So, again, type it in the original function, x plus 1, x minus 9, and then minus the 24, and then the 0. All right, so I'll just do a zoom 6. Now in this case, all I was looking to do is test to see if -3 was an eigenvalue. So I'm not even looking to see if the 11's on the screen. But if I wanted to adjust my window, I could. I just make my x max something bigger than, well, I'm kind of cheating. I know what the answer is, so let me make it 15. But it's parabolic, so I know I have to have at most 2 X-intercepts, so that's what I'm on the lookout for. All right, so what we do is second trace intersect, option 5. Then it asks me for the first curve, but what I want to do, and instead of answering their question, I'm going to ask them a different question. I'm going to do something different. I'm going to get over to where the intersection that I want to find is, because I'm finding the intersection between y equals this and y equals 0, which is the x-axis. All right, so if I get to this point, then look at the top of the screen, it says the y equals x plus 1, x minus 9, minus 24. That's my first function. Hit enter. Y equals 0 is my second function. Hit enter. So I clearly identify which functions I wanted to find the intersection of. And then my guess, which is very mathematical. But then again, that's kind of like what we were doing with the Markov chains. I took an initial guess, and then the iterative process carried me towards a solution. This actually is that thing I was talking about before called Newton's method. It's built into the calculator. So I hit enter, and it gives me my solution, the intersection between the 2 points, all right, or the 2 curves. So that's a technique that you could use to solve your equations, but maybe you don't want to do that because you're not confident that you can come up with a graph that would clearly show the intersection between the curves. Yeah, like if you have some crazy polynomial function, or when we talk about partials, some trig function, and you're like, I don't even know what this looks like. How am I going to come up with a window? Another technique that you could use, it's different depending on the calculator you have. Fortunately, I have many. You could use the solver function. So in the math menu, right in the bottom, there's an option called solver. All right. Some of your calculators say numeric solver. All right. So if yours says numeric solver, or if you have a color screen, then just sit tight. I'll show you in a minute on another calculator. But yeah, select that. And some of your calculators will bring up this display. So you might wonder, you know, do I have to do this? And I would say, keep an open mind. Because the number of times that I've gone through this process and afterwards a hand goes up, yeah, so, you know all that stuff you've been saying for the last 5-10 minutes? Can you repeat all of it? Because I didn't catch it the first time. And I was like, I know what happened. You didn't think you wanted to learn it. You didn't think it'd be useful. And now you realize it's a good way to do it. You want me to teach it again. And then when I call people out, we get a good laugh at it. But I think enough of you will like this approach that it's going to be worth it. So alpha trace y1 minus alpha trace y2. All right. This is what you're going to put in and leave in. All right. This is a function solver. All right. What it does is it takes the difference between those two functions and sets it equal to 0. So if you think about what we put in y1 and what we put in y2, that ultimately ends up being the left-hand side of the equation. All right. The reason why we want to do it like this is so that we allow ourselves to find the solution of any equation, even if the right-hand side is not equal to 0. All right. When you hit enter, it brings you to this. Now, it seems like it just told us the answer. It did not just tell us the answer. All right. Every time I go into this window from here on out, no matter what I put in for y1 and y2, it's always going to tell me that the answer is -3, unless I do something different. All right. X is x. All right, what I mean by that is when we found the intersection, the calculator solved for x. It stored that value in as x. So if I went into the home screen and hit the x key, the -3 would come up. 2 weeks from now, if I hit the x key, the -3 is going to come up. All right, so it just thinks x is equal to -3. All right, so we get that out of there and just put in some default value. For a quadratic, we expect there to be 2 solutions. Whatever number you put in there, the calculator interprets that as your initial guess. And what it'll do is it'll drag your solution, or actually it really is dragging you. It's dragging you to the solution closest to that number. All right, so there are 2 solutions. We know what they are, -3 and 11. By putting in a -10 and then hitting alpha enter, it's going to drag me to the solution that's closest to -10 out of those 2 possibilities. So alpha enter, it just dragged me to the -3. If there was a third solution, let's say a third solution was -12, it would have dragged me to the -12, all right? I got to know to be on the lookout for a quadratic for more than one solution. So what I would do is I put in something around -10, so let me put something around +10 and do the same thing. Alpha enter, it drags me to the solution closest to that. If you know that you're dealing with 2 functions that are only going to intersect once, doesn't matter what you put in, there's only one solution. It's going to drag you to the same solution no matter where you start. All right. So it's a pretty nifty technique because even if I put in, I have no idea what the answer is, -100. It might think a little longer, but it's still going to drag you to the nearest solution to -100. It can't get to the 11 without passing by the -3 first. All right, so it will always drag you to the nearest solution to that point. All right, this works for trig functions, works for log functions, pretty much anything you can think of. The only time it struggles is when there's discontinuities. So as long as you're mindful of those things, you're generally going to be okay. But the good news is it's not going to drag you to a solution that is at a discontinuity. So if you had something like a tangent function, when cosine's equal to 0, tangent doesn't exist. So it's not going to bring you to a place like if you're trying to solve tangent of theta equals 0, it's not going to bring you to like pi/2. All right, it'll never take you there. All right, because it knows not to do that. All right, so let me just show you very quickly on the other calculator. Almost everything is the same after you get your initial setup. Let me just get out of the glare here. All right, so math, numeric solver instead of solver. That part you probably figured out. Interface is a little bit different. So if your display looks like this, you actually have the better version because they created a little menu here for you to kind of have a little easier access. I mean, it basically is just going to take what you put in these fields and interpret it the same way we did in the other calculator. It's asking you for your first and second equations, right? For us, that means whatever is on the left and whatever's on the right. Alpha trace y1, alpha trace y2, set it and forget it. Those are things that you should never have to change. I have 37.5 in here from the last time I did a problem like this. All right, cool. Alpha, enter. It dragged me to the solution nearest to that number. All right, but you can see at this point it's the same process. Negative 212 is what I'm putting in. I have no idea what the answer is, so I'm taking a shot in the dark. Negative 3 is the one that's closest to that. More powerful memory, so it goes a little bit quicker, but it's still the same thing. Now you can see here it says bound. This is the calculator trying to say negative infinity to infinity. Right? So it's basically an unrestricted domain, but you can restrict that domain if you want. If you only care about positive values, let's say you're trying to solve for solve a probability question. All right, well, your answer is supposed to be between 0 and 1. So make your bound, instead of negative 1 E99 and positive 1 E99, make it 0 and 1. So that the calculator knows to only look in that interval. And then make your guess a number in between those two values. All right, it'll drag you to the solution. So it's a nice way to get around being bogged down by the algebra. All right, it's pretty nifty. And also, I mean, I don't want it. Well, I didn't come in here with the intention of getting completely sidetracked by this, but now I'm at the point where it's like, now I'm just showing off. Let's say you're taking like an accounting class and you couldn't remember your compound interest formulas. Actually, I'll tell you, any formula that's explicitly defined, so where you plug in numbers and you expect to get a solution that is also a number, you can use this solver technique to find the solution for you. So let's say you have, I'll do simple interest. Was it I equals PRT? I think. All right. What you can do is actually put these values in. With the old school calculator, what you'd want to do is subtract the I from both sides, because you need it to be set equal to 0. All right. So 0 equals PRT minus I. And so what you can do is in your your Y1, type in PRT minus I. All right, so that's Y1 minus Y2. That's the same thing as what I would have if I were doing a regular function-based equation. Now when I go into the solver, it gives me not only fields for a field for x, it gives me fields for every one of them. All right, so just think about any equation. Think of a science class where you have a formula where you have to plug in multiple values. Like you plug in 4 values and you're solving for the 5th one. There's 5 places where you could plug in a number. 4 of them, and you got to figure out the 5th one. You don't need to do algebra anymore. So the principle, the interest rate, but whatever. You plug in the numbers and then you solve for the missing one. So I'll just make up some things like 100.025, and then alpha enter on the one that you're looking for. All right, so it'll automatically solve it algebraically for you. So this is the closest the calculator gets to symbolic manipulation. All right, but very, very user friendly, provided you know how to use it, and you're friendly. Okay, so anyway, the next one, we start to jazz it up a little bit. Is 1 an eigenvalue of this? And if so, find the corresponding eigenvector. All right, cool. We're just gonna find the eigenvalues and eigenvectors. because these examples, the way they're phrased, they kind of assume that the previous page happened, you know, as in, like, you tried all those problems, we went over them together, but they were all typed, so we didn't. And so I'm using these problems as a way to introduce the concept. All right, so I need the determinant of the appropriate identity matrix multiplied by the scalar lambda, that minus this A. All right, this is what we're calling, again, A. So lambda I is going to be lambda 0, 0, 0, lambda 0, 0, 0, lambda. We're subtracting from that A. We don't really want to write the entire matrix again. Then we're finding the determinant of that, setting it equal to 0, and we're coming up with what, again, we call the characteristic equation. All right. So we're looking at lambda minus 4, 0 minus negative 2, so 2, 0 minus 3, so negative 3. So basically, lambda minus whatever's going down the main diagonal, and then reverse the signs of everything else. All right, so 0, lambda plus 1, negative 3, 1, negative 2, lambda plus 2. All right, so this is what we have to find the determinant of. And oh dear Lord, are we in for it? Because if we're going to find the determinant of this, we're either going to, well, we're going to do one of two things. We're going to put this in triangular form, diagonalize it. Well, we can't do that yet because we haven't learned it. So triangular form, because if it's in triangular form, you just multiply it down the main diagonal and call it a day, and that's your determinant. Or we're going to use cofactor expansion. All right. So the idea though is we want to pick a nice convenient row to work with, and so it appears in this case that the nice convenient row does not exist, but we'll settle for row 2. All right. So zero multiplied by, I probably shouldn't even write it there. I'll do it up here. Now, this is entry 2, 1, right? So negative 1 raised to an odd power is going to be negative, all right? So 0, though, it doesn't matter, but that's telling me that my alternating signs is going to be negative, positive, and so on, all right? So if we were in the first row, it would be positive, negative, so we got to be mindful of that, all right? So my second term or coefficient would be lambda plus 1. And then negative 3, but it's minus a negative 3, so plus 3, as it turns out. Smidge it over here. And so now I just need my ingredients. All right, so if I wipe out the row and column that 0's in, I get a matrix, but I don't care about that matrix because it's going to multiply by 0 anyway. So I'll just put a big old X in that. All right. If I wipe out the row and column that lambda plus 1 is in, then I'm looking at lambda minus 4, a negative 3, a 1, and a lambda plus 2. All right, if I wipe out the row and column and negative 3 is in, then I'm looking at lambda minus 4, 2, one, and negative 2. All right, so yeah, at least we got rid of one matrix. But ultimately, it's really not that crazy in terms of the act of finding the determinants. It's just solving the characteristic equation. That's where, you start to earn your keep. Now, imagine if you had to do it algebraically. Now, we'll see. Maybe it's a bad example. Maybe it's very easy to do it algebraically, and I'm just making up stuff as I go. So, lambda minus 4 times lambda plus 2, then minus a negative 3, so plus 3. Then I'm going to have plus another 3, but this time multiplied by I'm going to do 2. Nope. Yep. Plus 3 times, I'll write the negative 2 in front, lambda minus 4 minus 2. And that whole shabiggity bangity boom here should be equal to 0. All right. So you can go ahead and distribute all this out, or this one has too much glare. I just can't do it. This one, at least, the glare doesn't impact things too much. All right. So, again, my whole thought on this is, if I'm going to let the calculator do it, I'm going to let the calculator do it. I don't want to do any work. That's just a general rule of thumb. It just so happens life and linear algebra are coinciding tonight. So I'm just typing this in. Just everywhere I have the square brackets, I'm using parentheses, but still, it's the same. Same but different. I am blowing up here. Yeah, it's just mostly typos. It's like everybody from all of my classes are deciding to submit all of their typos right about now. What can you do? So I could look at the graph on this, but you look at what we see here, and it's like, maybe not. Maybe the solver is the way to go. So math, solver. Now, they told me a solution here. I just can't remember. Was it 1? Yeah, 1. All right, so I'm not really on the lookout for a 1, but I'll try it. I'll put in something close to 1. All right, so it verified the 1, which is great, because my big concern is that I did something incorrect leading into this step. All right, but the fact that 1 came up as a solution is pretty solid. But we do have some quadratic components in here, and we have an additional component right here that could lead me to believe that maybe this is even a cubic. All right, so now I want to see if there are even more solutions. So let me try something like, well, I put in a 2. Let me try something negative. All right, that's a lovely looking answer. All right, so I don't know what that's equivalent to. If it's a clean number, maybe it'll math frac. But the thing is, you should not really be expecting this to math frac, all right? Because what happens is the calculator is really working with an approximation technique to come up with these solutions. That's why the 1 came up as 0.999 repeated. So it's good enough to give you an idea of what the correct answer is going to be. Sometimes it'll tell you 2.000001, so you know that the calculator is trying to say 2, but that doesn't mean it's going to math frac to something meaningful. All right, but we have a solution of about negative 3.61. All right. So we know lambda. We knew lambda going in was equal to 1. Approximately negative 3.61. Now let's see if there's another one. Solver. Let me put in something large, like 20. Oops. And alpha enter. I got the same thing but positive. All right. If that one didn't math frac, there's no reason to think that this one would. It's the exact same thing. Sometimes it's subtly different at the end that you never know, but we could just pop the plus or minus on there at this point. Say it again? Square root of 13 is clean? Well, it is quadratic, so it makes sense to, oh, of course it is. The one thing I didn't check. So 1 plus or minus root 13. Yeah, so if something doesn't math frac, sometimes, most of the time anyway, it's because it's irrational, but sometimes it's because it's the square root of a number. So take that decimal, square it, and see what it is the square root of. Turns out in this case it's the square root of the prime number 13. So that's good. All right, so we have clean-ish values. All right, so now what we have to do in order to find the eigenvectors is solve the homogeneous equation associated with these eigenvalues. All right, so we're going to go back in time real quick and I'll show you the relevant. Yeah. Why did that not lock in? Well, I must have missed something here.
I think it turned on.
Yeah, but I can't even do anything with it now. And that's just going to aggravate me to see that there, like in my face the whole time. Right, okay. Oh, okay. So now I could just move it out of the way. Just chuck it up there. All right. So now what we're doing is we're taking this matrix and redefining it if, for example, lambda is equal to 1. My lambdas tend to look like x's from time to time, so you know, I'm intending for them to be lambdas, but if at any point you're not sure, just say something because it's kind of a big deal. All right, so we're looking at if lambda is equal to 1, we have -3, 2, -3, 0, 2, -3, 1, -2, +3. All right, we're solving the homogeneous equation, and we know that that just essentially means that we're just giving a column of zeros.
Is that one x? Is that x equal to 1?
Oh, that's just me being stupid. That's supposed to be a lambda. That one I have no excuse for whatsoever. Thank you. So, the trade-off, you know, like we get to do more, cover more, but you still have to type all this crap in. It's just, it is what it is. All right, so we're going to RF this bad boy. Good old RF, always coming back. An old friend. All right, math bracket. Ever so slightly changed. So 1, 0, 0, 0, 0, 1, -3/2, 0, and then 0, 0, 0, and one final 0. All right. So we're looking for the solution, and because it's very easy to lose sight of what we're doing here. This is the solution of the characteristic matrix multiplied by x. So this is lambda I minus a times x, this time it really is an x, equals 0. Poor quality lambda, so let me just fix that right quick. So lambda I minus a times x equals 0. So what we get as a result here is x equals. All right. So this amounts to x1 equals 0. x2 is equal to 3 over 2 x3. x3 is our free x3. So x3 is equal to x3. And so what we're going to get as a final result here for this particular eigenvalue, we will get the corresponding eigenvector x equals x sub 3 multiplied by 0, 3 over 2, 1. All right, so this is the eigenvalue, eigenvector with eigenvalue of 1. All right. But the issue is we have 2 more eigenvalues. All right, but it's not really that much of an issue because it's all calculator work. It's just we have to put in those eigenvalues in for A, matrix A, well, quote unquote A, it's really lambda I minus A, but we're replacing each of these with a radical 13 first and then a negative radical 13. But it's still the same stuff. It's just our answers aren't going to be quite as nice because we're dealing with a radical, but we can live with it. Right? So I'm going to steal the space for the next question. Well, I'm going to put a star on the next question because we're getting close. By the time we're done with this problem, we should be pretty much there. All right, so if we have lambda is equal to root 13, everything else in the matrix is going to be essentially the same except for the values along the main diagonal. All right, so it's going to be rad 13 minus 4. Then 2, negative 3. Then 0. Then rad 13 plus 1. Negative 3. Then 1, negative 2, and rad 13 plus 2. All right, so all I'm doing is replacing each one of these values along the main diagonal. I'm replacing the lambdas with a rad 13. All right, and then when we get around to it, we'll do the same thing with lambda is equal to negative rad 13. All right, so it's all going to be the same stuff, just with negatives. So negate main diagonal. Well, negate the negative 13. I don't even have to write that now that I think about it. I'll just snip what I put in the calculator. But go into my matrix editor, and I'm only just changing 3 values. So I'm drastically changing them, sure, but it's only 3 values. So radical 13 minus 4 converts it automatically to decimal form. All right, radical 13 plus 1. Same deal, automatically to decimal form. Radical 13 plus 2. All right. There's no reasonable expectation of a math frac here when we do the RF, so we're just going to go with the decimal values. But we'll copy paste. I mean, you could try to math frac it, but again, no reasonable expectation. No change whatsoever. All right. So I'll just do a quick snipperooski here. I'll edit it, but then I'm not going to paste it in because then what I'm going to do is simultaneously handle the other one. Oh, it's done. I still want to save the photos. All right. So then back into the matrix editor. So this entry is going to be this negative square root of 13 minus 4, negative square root of 13 plus 1, and then negative square root of 13 plus 2. All right, so we run those numbers again, but this time I'll actually snip this matrix and put it in there because I didn't write it out. All right, so ref that, and we get this bad boy. All right, so picture existing. So that's that one. Cockeyed, but it's all right. All right. Still a little, whatever. All right, so now we just want to state the eigenvectors that are coming from this. So this is, again, the matrix equation. Both sets of matrix equations associated with the eigenvalues, specifically of rad 13 and negative rad 13. And so this is the ref variation, both of them. All right, so pretty ugly, but we can get a pretty easy way of representing these because as it turns out, in each case, the free variable is the third entry, which would be in each case x3. And all we're really doing is negating the third entry, which is corresponding to x3, so we're in good shape. So x as a solution for the second eigenvalue should be equal, and we're going to approximate x3 negative 4.30, I'll say 303, positive 0.651, and 1. All right, because again, that free variable of x3. All right, so it would be the same as if I wrote it out just like I did right here. The free variable gets the coefficient of 1. So x3 equals x3. So that's the same thing that happened here. And these other ones, they just, well, this one was a 0. This one just got negated. All right, so that's all I'm doing here. So I'll do the same thing down there. And we can kind of, sort of cut to the chase a little bit. All right, so these are the three eigenvectors. Because what happens is when I show the intermediate step of writing it as x equals 0, x1 equals 0, x2 equals x2 equals 3/2 x3, it comes from adding this term to the other side of the equation. And so here I have a positive value that I would be adding to the other side. Subtracting from the other side, and a negative that I would be adding to the other side. All right, so it's just the operation that's changing the sign. All right, so depending on what we're using this for, there's a variety of different ways you can represent your eigenspace. Even though they're not asking us specifically in this question, there's a lot of things they weren't asking us for. So the reality is, if you really think about it, based on what the question was asking us, this, and this was all I needed to do. All of this other stuff was for me to teach you things, all right? Because you're going to need to know it anyway, so I figured no time like the present, all right? So the basis of your eigenspace would be these three vectors. Doesn't matter what order. When we learn next class about how to diagonalize a matrix, and then all the wonderful things that happen, well, not really happen, but all the wonderful uses of that concept, then you'll see that the order in which you represent your vectors will be important. But for now, not so much. All right.
Question. So if we're extending that logic and saying that the basis of the eigenspace is the space formed by all the eigenvectors for the problem.
Then the next question is flawed. Yeah, I just saw that too. Whoop.
Well, what's actually funny is that you get a repeating 3 when you solve the polynomial.
Oh, I don't even remember that.
I have no idea to do it, but you get a repeating 3.
Well, it's just going to correspond to the same eigenvector, so it's fine. Right.
It technically does mean that the space then would be only the basis of that space would just be then the singular vector.
But there should be, because it's three-dimensional, there should be, if you have, is it repeating three times? So 2 times, so there should be a third one. I'm sorry, a second one that is unique.
Would it be the 0 vector?
Well, if it is, then that's a problem, but.
I mean, I don't know what else it could be if you go through.
Right, I mean, it could be an eigenspace, but it wouldn't, it would have to be a subspace of the real space. So it couldn't form the basis of real space. It would have to form the basis of a subspace rather than the entirety of the, which is fine. It's just not quite what I had in mind when I created the problem. So, but we'll tackle that one. So we have a three-dimensional matrix. So if we're going to find the determinant of, it's going to be the identity matrix in 3 dimensions multiplied by lambda minus a. We're going to set that equal to 0. So we're looking for, again, the characteristic equation. So basically, as a shortcut, what we were talking about last time was we're subtracting the diagonal entries from lambda and negating everything else. Right. So we have to expand this with cofactors. Expansion by minors is another way of saying that. So working across the first row seems to make the most sense. So I'd have a lambda minus 4 multiplied by the 2 by 2 matrix that results if I were to remove the lambda minus 4 row and column from the matrix. So lambda negative 3 2, and lambda minus 5 would remain. All right, minus coefficient there would be 0, so it doesn't matter what the matrix is. So I'll just put an X there because it's going to be irrelevant. It's going to zero out anyhow. Plus, the last one would have a coefficient of 1. If I remove the row and column that contains the 1, I have a negative 3, lambda, negative 2, and positive 2. All right, so now all I have to do is not screw up the algebra. All right, for me that's easier said than done. So lambda minus 4 is going to be multiplied by this determinant, which is going to be comprised of the diagonal down product and the diagonal up product. So lambda squared minus 5 lambda minus a negative 6, so plus 6. Then we're going to have a minus 0, so irrelevant. We're not going to bother with that. The next piece will be negative 6 minus negative 2 lambda. All right, so so minus 6 minus negative 2 lambda, so plus 2 lambda equals 0. All right. Now I mentioned that, you know, sometimes it's just a pain to type it, but there's no reason why you should have to do any of this by hand. All right, so I'm going to go right to the calculator and get a measure of lambda and hope for the best. So I'm just going to type in x instead of lambda minus 4 times x squared minus 5x plus 6 minus 6 plus 2x. All right, and the other side I make 0. That's assuming I want to use the solver. I could use the solver, I could use the graph. Sometimes just looking at the graph makes all the difference in the world, because if I look at the graph here, that's a fortunate window. I had the proper zoom and then I messed with it. So it looks like it's crossing through at 3. Now what I would want to see is whether or not, so that intersection would be at 3. I want to see whether or not there's another intersection. All right, so just zoom out. I think I've sufficiently zoomed out. I mean, a lot easier to do it on my device than on yours, but it gets the job done either way. The journey back in is a little bit more difficult for me than it is possibly for you all. But it is pretty clear that this is well, it looks like an odd function, all right? And if I were to distribute it out, it would end up being a cubic function just because I have a lambda multiplied by a lambda squared. All right? After combining like terms, it's still going to be cubic. So we're going to have an odd number of roots. All right? So we could have at most 3 roots, but only odd numbers. All right? That's how cubic functions work. All right? So if I had an even power, then I could have any number of roots up to whatever that power is. But it also depends on sign changes, and if you even learn the Descartes rule of signs, then I'd even be shocked about that. But you know, there's enough evidence to say that we're pretty satisfied that there's only the one root here. All right, so one real rational root. The other 2 roots would be imaginary, right? And we could flesh out what those are, but it doesn't really add anything to the situation, because the eigenspace is going to occur in real space. All right, there is a complex space that you could focus on, but that's not related to the eigenspace. All right, so what I would do now is pop that 3 into the characteristic matrix. So at lambda equals 3, and that was given to us. But I mean, the hardest part I think about any of this stuff is coming up with the eigenvalues that lead to the eigenvectors. So it's really worth your time to really flesh that out. So plugging in the lambda equals 3, -1, 0, 1, -3, 3, -3, -2, 2, -2. All right, we're solving the characteristic equation. I'm sorry, the characteristic matrix as part of the homogeneous equation. And so that's just going to require a little ref action. I'm going to find out in a second if I... Yeah, it would have been nice. Sometimes I have the, surprisingly have the matrix stored in. I was hoping. From a different class. Just doing a little double check of Ruski here. Looking good. So, little ref action on matrix A. And we get this mamma jamma here. All right. So we're looking for the basis of the eigenspace related to this matrix. All right. So since we only have one eigenvalue, there's only going to be one eigenvector, but we should still state what that is. All right. So this is the same as saying x of 1 minus x of 3 equals 0. X of 2 minus 2x of 3 equals 0, and x of 3 equals x of 3. All right, so this goes all the way back to, I think, unit 1, if I'm not mistaken. X of 1 equals x of 3. X of 2 equals 2x of 3. And x of 3 is equal to x of 3. So that's telling me that x is equal to x of 3 multiplied by 1, 2, 1. All right. So this is the eigenvector with eigenvalue equal to 3. All right, since it's the only eigenvalue corresponding to the only eigenvector, this forms the basis for the eigenspace. All right, so the basis for this eigenspace is the vector 1, 2, 1. All right, because everything would be a scalar multiple of that. All right. Now, the eigenspace in and of itself is a subspace, so we wouldn't expect to be able to span out all of real space dimension 3 using this single eigenvector. All right, we would need more than this, but this is enough to get us through our relevant eigenspace, which is a subset of that real space. All right. So, you know, I mean, you look at what we just did here, it's a fair amount of work, but based on the question that was given and they gave us the eigenvalue, you know, a lot of it didn't technically need to happen, but it's all definitely worth taking the time, you know, get the concept down. So some of the questions here say find the eigenvalues, some of them say find the eigenvalues and eigenvectors. As you have just discovered, eigenvalues, not too bad. Eigenvalues and eigenvectors, finding them all in one shot, it's a fair amount of work, but it's definitely work you want to put time into determining the values of, or at least the process for, because it's pretty important stuff, and it's critical to understand this going into what some of the problems on the previous page, if you still are conscious. All right. So then number 4, find the eigenvalues. All right, so it's same general idea, except we have a cleaner looking matrix here. Cleaner meaning there's more zeros involved. So in theory, that means that things should be a little bit more streamlined. So we're looking at lambda minus 5, 0, 0, 0, lambda 0, 1, 0, lambda minus 3. All right. Now, this is a situation where, well, I'll carry out the process and I'll show you the shortcut through the maze here really quickly in a sec. But let's say I work through row 1. I would say lambda minus 5 multiplied by lambda 0, 0, lambda minus 3. All right. Which corresponds to lambda minus 5. Diagonal down minus diagonal up is going to be lambda times lambda minus 3. All right. The shortcut through the maze here, it's kind of a nice situation. But if you don't pick up on it, you can see that we didn't pay a hefty price for it, because the other 2 coefficients would have been 0 anyhow. So I didn't have to worry about creating 3 additional matrices. All right. The shortcut is that since this is a lower triangular matrix, it's kind of hard to, well, I'll use a highlighter. All right, it's lower triangular. All you have to do to find the determinant is multiply down the main diagonal. All right? If it were upper triangular, same deal. Any kind of triangular matrix, just multiply down the main diagonal and you'll have the measure of the determinant. All right? If it's a diagonal matrix in and of itself, that's even better. You're still just multiplying down the main diagonal. All right? So bottom line is you could just grab your eigenvalues right out of this because there's really no work to do. Lambda, poor quality lambda, is equal to 5, 0, and 3. All right. So we found the eigenvalues. All right. But I kind of can't stop myself. We're going to find the eigenvectors that go along with those eigenvalues. All right. So just because while we're here, we might as well. And you know what? I'll even take it as a typo. So, using the characteristic matrix, I'm going to pop in first a 5. So at lambda equals 5. We'd have 0 across the top row, 0, 5, 0, 1, 0, 2. And that would be now this is pretty much already in, it's not quite the echelon form, but it's close enough that you could probably do this one by hand and be pretty satisfied with your answer. Because if you just swap the first and third row and multiply the second row by 1/5, it would be pretty much there. All right, but you could also, there's no need to do it by hand. You could just do it in the calculator. All right, so, but I'm going to set up all the homogeneous equations first. All right, so -5, 0, 0, 0, 0, 0, 0, 0, oh, nope, 1, 0, -3. All right, then the last one, -2, 0, 0, 0, 3, 0, 1, 0, 0. All right, so we have each of these eigenvalues, and from those eigenvalues we'll have the corresponding eigenvectors, which would give us the basis for the eigenspace. All right, a lot of eigen this, eigen that, eigen everything. All right, so if you're going to do one of them in the calculator, might as well do them all, or maybe not. I don't know. I don't want to make that judgment for you. You decide. I mean, because there's also the I don't really know what it's called. It's just I'll call it a testing phenomenon, because it is singular. Things that don't happen every other time you tackle a problem, for some reason happen during a test. Like you don't make a mistake ever, but then the one time you have to do it on a test, all of a sudden you just can't get it right, Like it's just some sort of phenomenon associated with just test taking. It's kind of like the placebo effect, but instead of a placebo, it's a test. It just is what it is. So, maybe you can do it by hand, but maybe you do it on the calculator just because you're like, I'm not taking a chance on this. What are you, crazy? You could also go the other way. You see, I almost screwed that up, and say, you know what? I never accidentally type things in incorrectly on my calculator, except the day I'm taking a test. So maybe I'll type it in the calculator, but I'll also do it by hand if I have a few extra minutes. But just as I predicted, swap the first row and the third row. It wasn't really a prediction. It was just like a statement of what it was going to be. Swap the first and third row and multiply a second row by 1/5, and you have it. So it's really just a matter of rewriting one way or the other. Kind of dealing with that test phenomenon with my son now. For the first time, he's making like dumb mistakes on tests, and he's like, I swear I didn't write that. And I'm like, yeah, you did. You just didn't realize that that's what you were writing. You thought you were writing the right thing, and you wrote the wrong thing. It happens, He's like, there was one moment where he's like, I think the teacher might be changing my answer. And I'm like, your teacher is not changing your answer. I don't think, anyway.
You want the first unit circle for cosine and sine of the body, I put square root over 2 over square root over 2.
Oh, you put that radical.
I wanted to make 1, so but I didn't realize.
And like every other time you do it, you never make that mistake, right? Yeah. And you're like, where'd that come from?
It's like some like if you cancel square root over square root, it's gonna be 1. So I never realized it.
The one thing about these calculations, it's kind of mindless. So, you're just changing some values as you go along. It's just, the more times you have to reproduce something, the more chances there are that there's a mistake in there. So you just got to be really careful. Like copying and pasting. 1, 0. All right, so we just want to make a statement of what our results are really telling us. And this, I find, is where when people make a mistake on this is where it tends to happen. Because you really want a shortcut here, but the shortcut can sometimes work against you. So I'll talk about that in a sec. So we know it's going to be x1 plus 2x3 is equal to 0. x2 is equal to 0. And x3 is equal to x3. All right, and that in turn corresponds with a matrix, or I'm sorry, a vector function x equals x sub 3. We're really just, well, let me not skip it. I was about to skip it and show you where the pitfalls were, but let me not skip it on this one. And then I'll still point out where the pitfalls are. So x1 equals negative 2x3. x2 equals 0. x3 equals x3. All right. So what's really happening here, if you look at what we had in our original matrix and what we have in our solved set of equations here, we're taking the reverse of any signs that are in the last column. The only exception being the last entry, because the last entry is a free variable related to x3. So that is the case where we have a coefficient of 1. All right, but what happens is when people start falling in love with shortcuts, they end up making that a coefficient of 0 also. So this should be x equals x sub 3, negative 2, 0, 1. All right, so if you're going to apply a shortcut here, that's fine, as long as you are mindful that that last entry is not really a 0. All right, because it's x3 equals x3, it corresponds to a coefficient of 1. All right, so for this one, I would say x equals x3 times, it's a safe bet, x1 equals 0. I mean, x1 equals 0, x1 equals 0. All right. Then we have x3 is equal to 0. Actually, this is a weird one. Hold on a sec. I don't even think I could use a shortcut on this one, because we have no solution for x2. So it actually turns out that x2 is the free variable in this one. All right, so I'm actually going to write this one out also. Not going to take any chances here. All right, so x1 is equal to 0. x2 is equal to x2. x3 is equal to 0. All right, so that gives us 0, 1, and 0, yeah. X3 is going to be equal to 0 because in this entry here, I just wrote it out of order, but in this entry here, because there's no pivot in the second column, there is no x2 equals. So it must be x2 equals x2, with this one being the x3 that's equal to 0. All right, so this entry, because I wanted to write it in the proper order, but this entry here corresponds to this one. Oh, poor quality. So that last row must have been the case where, my highlighting is not where it should be. It's just out of habit. Oh, now I'm locked in. Oh, that's rough. Kind of bringing it back. All right, so because x3 is accounted for here, it must be the x2 that's the free variable. All right, so that leads to this one. Maybe that's why this question was only asking for the eigenvalues. All right, but it's still good. All right, because x2 is just referencing a scalar multiplier of the basis vector 0, 1, 0. All right, so we have two bases already accounted for, negative 2, 0, 1, 0, 1, 0. All right, so now the last one is in the proper format, so we could just kind of cut to the chase. So I think I'm just doing a pretty good job of proving that shortcuts are not a good idea for this. So, and staying away from them is probably the best idea. cutting corners, etc. And so x of 3 is equal to x of 3. And so we have x equals x of 3, 0, 0, 1. All right. So the basis for my eigenspace -2, 0, 1, 0, 1, 0, and 0, 0, 1. All right, now depending on what we have to do with that, you know, we could write that as its own matrix. You know, if I needed to find a set of weights that would be a linear combination of these three basis vectors to give me a brand new vector that is in the span of this eigenspace, then I could do that pretty easily. So it's just solving another linear system. So there's a lot of things that we can do with this. It's just basically, if you really think back to the beginning of the course, when I would give you a matrix, it was like just out of nowhere. It wasn't defined in any capacity as part of like a contextual situation. It wasn't part of a linear system, as in like you had 1x1 plus 2x2 plus 3x3 equals 0. You know, there wasn't anything that came from like finding the intersection between lines in space. It could have been a set of eigenvalues that led to those basis vectors. So when we were trying to determine if a vector was in the span of a given set of vectors, maybe those were eigenvectors, right? So, you know, these aren't too crazy to look at, you know, like when you see them, it's like, they look like any other vector. It's just a question of, you know, what's so special about these? And again, eigenvalues and eigenvectors are vectors that won't get knocked off their span when they're operated upon, right, for a given operation. Right? So if you wanted to transform a vector, these are the ones that are resistant to that transformation. The only way they would differ from their original values is by some scalar lambda. All right. So the next one is pretty much the same concept. Actually, the next two. So I feel like 18 to 20 minutes in, I might be beating us to death a little bit. But so what I'll do is I'll just attach a couple of stars onto these, and we'll save them for another time. Because what we're about to learn, something called diagonalization, you guessed it, involves finding eigenvalues and eigenvectors. So we're about to do the same stuff again. So it's not like we're skimping out on the work too. I just want to get to diagonalization because this is the important concept for tonight. So when we go back and tackle those other starred problems, I'll pick up some of those other concepts. But now that you have a better sense, because I know the last lesson was a little, you know, I don't want to say all over the place, but I don't know what else to say. So it's like, it took a problem and it's like, there's an inch of space to do it in, and somehow I made it take up the entire page. So, you know, hopefully the second look at it is a little bit nicer. And this should be even better. All right, so definition of diagonalization of a matrix. A matrix A is diagonalizable if there exists a non-singular matrix. All right. So an invertible matrix, P, and a diagonal matrix D such that this equation, this relationship applies. All right. So, and really, if you think about it, you're applying some non-singular matrix multiplication to matrix A, and then really undoing that by multiplying by the inverse of matrix, that invertible matrix P. Right? So, because really, if you consider what's going on here, these two, the inverse P and P itself, they should offset each other. So we're looking at equivalent relationships, D and A. Right? So this is the key ingredient. An n by n matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. All right? So the key here is that we're looking at an n by n matrix. So an n by n, but I'm going to emphasize the second n. That's telling us that the number of columns in your original matrix A should correspond to the number of eigenvectors. Well, eigenvalues given the eigenvectors. So we need as many eigenvalues as there are columns in the original matrix. Otherwise, it is not diagonalizable. All right, so, you know, if they go over to a test, determine if, not find the diagonalization, but determine if the matrix is diagonalizable. All you gotta do is find the eigenvalues, all right? See how many there are. Because if there's only one and it's a 4x4 matrix, then you're done. Okay, you don't have enough eigenvalues to correspond to eigenvectors to fill up the entire space. All right. An n by n matrix may fail to be diagonalizable since not all roots of its characteristic equation are real numbers. So if you get complex roots like that one that we started off with, where the lambda value was given as 3, the characteristic equation had a power of 3, which means that you could have upwards of 3 real rational roots. All right, but since we only had 1, that means the other 2 had to be complex. They had to be imaginary. All right, so if you have a 3x3 square matrix and you only have 1 real root, that's the end of it. Now, the exception is the triple root. Right? It is possible that your cubic function could just be a binomial raised to the 3rd power, in which case you have a triple root. That's fine. All right? It's when you have complex roots in there, that's where you have a problem. All right? It does not have n linearly independent eigenvectors. Right? So that's something that we're going to have to look at. All right? So here we're starting off with a 2x2, so pretty, call it basic. All right, because the calculations won't be too crazy. But still, it's a pretty involved process because we're finding eigenvalues, eigenvectors, and then some. All right, so we set up our characteristic equation. So we're looking at lambda plus 4, 6, negative 3, and lambda minus 5. Diagonal down minus diagonal up, so it's still going to be quadratic. Or, I'm sorry, it's still going to be polynomial. Dimensions determine what type of polynomial function it is. Minus a negative 18, so plus 18, is equal to 0. Now again, put it in the calculator if you want. I mean, if you like doing the algebra, that's fine. But I'm showing you this, I'm encouraging you to do it this way so that you don't get bogged down with the algebra. All right, there's no reason for that. All right, but the exception would be something that has like, you know, some funky fractional or radical root, but I'm not gonna do that to you. All right, so that one problem, which really kind of, it was like the casino world in The Last Jedi. It brought the movie to a grinding halt. All right, that one problem that we did last class where 2 of the eigenvalues were, one was radical 13 and the other was negative radical 13, it brought the class to a grinding halt. It's like, oh, now we got to plow through this. That was the casino planet. All right, so not going to do that to you, okay? So the eigenvalues are going to be clean. I'm not going to say they're going to be whole numbers. I mean, it could be a half unit, but if it's a half unit, that's something you could pick off a graph too. All right, so you look at it and we see we have a clean -1 and +2. All right, so could you have figured this out pretty easily by hand? Sure, but you could also figure it out pretty easily without doing it by hand. So I can just write the answer down, whereas maybe some people are distributing and playing around with different possible factors. I don't have to bother with that, so I didn't. Right? Because you're going to pay the price for the work anyway. I mean, now we have to come up with well, we already have matrix A, but we have to come up with P and the inverse of P, all right? So we think about what that would be. Form the P and D matrix. The D matrix is just the eigenvalues down the main diagonal. Okay, that sounds great, right? The P matrix is a little bit different because what that is the eigenvectors placed in the same columns that the eigenvalues are placed in, all right? So I can immediately right now state what my D matrix is going to be, my diagonalized matrix. It's going to have a -1 and a 2 down the main diagonal, all right? D for diagonal, all right? But what this is telling me indirectly is I got to find the eigenvectors, all right? Step 1 told me to find the eigenvectors. Step 3, for some reason, I can't get out of my own way. I know what I did. It used to be step 1, find the eigenvalues. Step 2, find the eigenvectors. And then I was like, oh, I could just combine that into one step and save myself some time and some space. But I just didn't change the numbering. So that's a typo for someone. So anyway, let's focus on lambda equals -1. So 3, 6, -3, -6. All right, now this, and it's pretty rare that this happens, this is actually one that you probably could and should be able to do in your head. Right? You're welcome to, I mean, of course, always use the calculator if you'd like. But just by adding row 1 to row 2, I cancel out, and you don't have to show me the steps. So by adding row 1 to row 2, I would cancel out that bottom row. It would go to zeros. By dividing row 1 by 3, so multiplying row 1 by 1/3, it would become a 1 and a 2. So actually able, I mean, it's kind of nice. I mean, how often does that happen? To actually able to come up with the row reduced form of a matrix in your head without even considering putting it in the calculator. That's kind of a nice feeling. All right, but it only happens because the second row is the exact opposite of the first row. All right. Every other situation, almost every other situation, we'll see more in a few minutes, but almost every other situation, you would most likely say, okay, well, I'm not taking any chances here. I'm putting it in the calculator. All right, so this is saying x1 plus 2x2 is equal to 0, and x2 is equal to x2. So we're looking at x. Again, I'm not going to skip it. Do a different color though. x1 is equal to -2x2 with x2 equal to x2. And that gives me the x equal to x2 times -2, 1. Okay, assuming my pen wants to work. All right, so that's my first eigenvector. Now I need my second one, which comes from popping a 2 into my characteristic matrix. All right, and if you put in the 2, you see what you get on the top is a couple of 6s, a pair of 6s, and then a pair of -3s on the bottom. All right, so for the eigenvalue of 2, again, it's probably something that you could do on the fly, because if you double the second row and multiply it by the first one, that's going to zero that one out. And then you can multiply the second row by -1/3. And then from there, it's just a matter of swapping them. So you should come up with 1, 1, 0, 0. A couple zeros on the outside. it's not always the case that that happens, so you know it's kind of a feel-good story when it does. All right, so x1 plus x2 equals 0, with x2 equal to x2. All right, and so we're looking at x1 is equal to negative x2, with x2 equal to x2. And so we're looking at the eigenvector x2 against negative 1, 1. All right, and again, we just want the bases of these eigenvectors. All right, so the fact that you can multiply each one of these eigenvectors by any scalar multiple, that's immaterial because I want the basis, which is just the vectors themselves. All right, so, well, actually, I'm going to need that calculator in a minute. So I have my D, because again, those are the eigenvalues down the main diagonal. So we're looking at D is going to be the matrix negative 2, 0, 0, I'm sorry, negative 1, 0, 0, 2. And my matrix P is just going to be the set of eigenvectors, right, in the corresponding order. So the eigenvector of negative 2, 1 came from the eigenvalue negative 1. So it's got to go in the same column. All right, so negative 2, 1 has to go in the same column. The other eigenvector, negative 1, 1, came from the eigenvector of 2, I'm sorry, eigenvalue of 2, so it has to go in the same column. So now I have my matrix P. All right, so what we want to know, because I mean, they just said, find the non-singular matrix P and the diagonal matrix D such that this relationship is true. All right, well, cool. I mean, we found them. It's just a question of whether or not that relationship is true. D is just the eigenvalues down the main diagonal. So I had two eigenvalues, negative 1 and 2. So I'm just writing them down the main diagonal. It's going to be a diagonal matrix, so every other entry is going to be 0. Okay. Then the P comes from using the eigenvector that corresponds with the eigenvalue used here and placing it in the corresponding column. So this eigenvector went with the negative 1, so it has to go in the same column as negative 1. And the same goes for the other one. All right. So what I want to do in my calculator is see if D is equal to inverse PAP. So I'll make matrix A matrix A. Which is negative 4, negative 6, 3, 5. All right, so that one's good. Then matrix B, I'll make P. That came out wrong. All right, so in my calculator, I'm actually going to do inverse BAB. Ah, dang it. Well, actually, I should probably double check it anyway. Okay. Inverse B, matrix A, matrix B. And that should come out to my diagonal matrix. And it did. So it checks. So it done did it right. That's great news. right? So now what I can do is actually put this to use, because one of the properties, now arguably a lot of the, I mean, this whole, let me pause this, really badmouth the content while I was recording it. So we have a relationship that we know is true, right? A to the k is equal to p times d to the k times the inverse of p, right? So if I want to find a to the nth power, it's going to be this relationship, all right? Just in a different order, because what we're doing is we're really just kind of solving for a different variable, all right? So if I want to find a to the nth power or a to the kth power, it doesn't matter. I'm just going to do everything in the reverse order, all right? So instead of multiplying first by the inverse, I'll multiply by the actual p. So we're looking at a is equal to p d inverse p. And then what ends up happening is if I'm looking for something like a to the nth or a to the k, like in the rule, since these two things offset one another, these two are irrelevant to the calculation, right? So what that's telling me is that all I'd have to do is find what d to the nth power would be, multiply it by p and then the inverse of p, and I'll have a to the nth power, right? So the reason why that's a good thing is because it's very easy to find a diagonal matrix raised to a power. I'll just give you a quick example. So, I'll just do it on the calculator just so to make it easy. So let's say I had, where did I put matrix? Oh, well, matrix D is the result, right? So I'll just store that in as matrix C. All right, so if I did matrix C, I'll keep it simple to like the third power. All right, you can see, hopefully, that all you're really doing is taking the entries along the main diagonal and cubing them. All right, but then let's take a look at what happens if I were to find matrix A. All right, that's this matrix cubed. It's not simply a matter of just cubing each of the entries, right? So for any non-diagonal matrix, you can't just cube the entries and be done with it. You can't even just cube the values on any of the diagonals and be done with it, right? I mean, there is a relationship here where it seems that you're tripling the values on the diagonal up, but that's really all you can get out of this. But you can cube the values along the main diagonal. So what we do is we figure out the diagonalized form of a matrix, raise that to whatever power we want, and then multiply it by the P matrix and its inverse, and that gives us the equivalent to matrix A being raised to that power. All right? It's designed to be a more convenient way of calculating this sort of stuff. But again, by hand rather than doing it in the calculator. All right, so, because again, if I just showed you, I could take A and raise it to the third power, right? But if I took that D, the corresponding D, raise it to the third power, which I did over here, then what I would do is multiply it by, well, B. Let me save this as D so it's a little bit nicer. So I would take my matrix B, which is equivalent to the P that I have on paper, you get the same thing that we got before, negative 10, negative 18, 9, 17, but the theory is that this would be an easier calculation to do by hand. All right, so it's fun math, really, more than anything else. So when I say is the matrix diagonalizable, we're really just talking about whether or not there are distinct eigenvalues that can come from this. So lambda minus 5, 3, negative 3, lambda plus 1. Characteristic equation, lambda minus 5, lambda plus 1, minus a negative 9, so plus 9. Again, just to save yourself from having to bother with this, you just put it in your calculator. Alright, so it looks like it's a 2. If you simplified it, you'd see that there's a double root here. Alright, so we're going to have lambda equal to 2. Alright, and so it's a double root. And so we're only going to get a single eigenvector out of this. So, you know, I might as well just show you. Alright, so we'd be looking at negative 3, 3, negative 3, 3. Alright, you can cancel out the bottom row immediately. And then multiply the top row by negative 1/3. Or you could just put it in your calculator, but we know the bottom row is going to cancel out. The top row is going to go to 1, negative 1. All right, so you'd be looking at x1 minus x2 equals 0, and x2 equals x2. So that's the same as saying x1 equals x2, and x2 equals x2. All right, so x would be equal to x2 so we'd get 1, 1. So now it's just a question of, is this going to be a meaningful diagonalized matrix? All right, so we can investigate. We'll take a look, and then we'll generalize. All right, so we only have one lambda value to work with, which is good because it saves us the calculations anyway. That's for lambda equals 2. All right, so my D matrix it's a double root, so we'd have 2 down the main diagonals. Poor quality lambda, so let me fix that. It just looks hideous. And so my matrix P would be 1, 1, 1, 1. All right. So herein lies the problem. So when I go to find the inverse of P, right, I can do it on the calculator. You can do it by hand, but you're going to get the same result. So I'll just put it in on the calculator just so you can see quickly. So 1, 1, 1, 1. You get a determinant equal to 0, all right? But even more so, I could just say, go ahead, find me the inverse. All right? It has a problem, well, my calculator has a problem, because it's telling me that the inverse of the function is the matrix is the function matrix itself, and that's, you know, I guess that's conceivable. You know, if you're talking about the identity matrix, an identity matrix is invertible and it is its own inverse. That's wonderful, but that's not the case for non-identity matrices. All right, so the calculator is having a hard time with this. If you think about the rule, the shortcut rule for finding the inverse of a matrix, a 2 by 2 square matrix, it's 1 over the determinant. All right, so what my calculator should have said was error, undefined. Maybe that's what yours would say, I don't know. But this is not an invertible matrix. All right, so there's no way, there's no possible P inverse. And so what that tells me is that A is not diagonalizable. All right, it's not diagonalizable. I don't even know if I spelled that right. I've lost interest. All right, so I definitely did not. There's no E. Well, good thing that word wasn't on the 4th grade spelling bee championship of Dutchess County. Otherwise, I wouldn't have been the 4th grade spelling bee champion of Dutchess County. No big deal. So, double root, that's the problem. So what we need are, again, if we have n columns, so n by n matrix, you have n columns. The number of distinct real eigenvalues must be n. All right, so I have 2 columns here. I need to have 2 unique real eigenvalues. All right, I do not have 2 unique eigenvalues. I have 2 eigenvalues, but they're not unique. All right, just because there's a double root does not mean that it's something that occurs multiple times, at least in this context. All right, so double root in algebra means pretty much the same thing that it would mean here. You have a single x-intercept, a single unique x-intercept. All right, we have a single root. All right, so it's not, we don't have unique eigenvalues. If I had, let's say, a cubic polynomial eigenvalue equation, and it ended up being a triple root of the lambda equals 3. All right, that does not mean that we have 3 eigenvalues. It means that we have 1 eigenvalue that's been replicated a total of 3 times. All right, so it's in this step here that we could have said, not going to work. And it's really, I just kind of highlighted the wrong thing. It's the double root aspect of it. All right, so we could have stopped there, but I wanted to show you that, like, all is not lost on a test if you don't recognize it here, because at this point, you go through the process and you realize, it doesn't work. Why doesn't it work? Oh, dang it, it wasn't diagonalizable, which is kind of the point of the question to begin with. All right. Honestly, I mean, you probably already guessed this, but on the test, when I ask you to determine whether a matrix is diagonalizable and justify your work, the answer is no, it's not diagonalizable. You just got to show me the supporting work, right? Because I'm not going to ask you just to determine if it's diagonalizable and have it be diagonalizable and then not have you diagonalize it. You know what I'm saying? So you'll have a separate question where you have to actually diagonalize it. All right, so I'm kind of giving the shop away here, but it's something. All right, a little application to calculus. This stuff's pretty not bad so far. You know, like, we'll get to some other calculus related topics next week, but this is kind of the lead-in. Hopefully this is the next page. Yeah, because just trying to remember, because I made some edits. Yeah. So what we're going to do is learn some basic derivatives and antiderivatives related to linear algebra, and then linear regression. And then we'll learn about partial derivatives, and we'll kind of tie it all together. That's going to be the penultimate, well, this is the penultimate, of course. All right, so how can we use our knowledge in linear algebra for other classes? Right? It's kind of interesting to think that it's even possible. And with that in mind, I'll give you the idea that differentiation and anti-differentiation is really just another transformation. All right, so when you're working with a polynomial function, what we're trying to do when we find a derivative is we're trying to transform that polynomial function into the vector space related to derivatives. All right. So all we would really need to do is define a vector space related to any kind of derivative that might exist for polynomial functions. All right, we're pretty much going to stick with polynomial functions because trig functions, I mean, we'll get to some trig, but for the most part, polynomial functions are where it's going to be at because they tie together nicely with what we've been doing. When we cover partial derivatives, we're not going to get too crazy into that because that's more Calc 3, but we'll get into like the basics of it. All right, so it's kind of like I'll call it a primer or a teaser for Calc 3 if you haven't taken that course yet. You'll get a sense of what you're up against. It's not anything too bad. All right, so at least that part of it. So what we want to do is define what the vector space related to the first derivative of a function might look like. All right, so the standard basis for any polynomial space would be, well, you have the constant, you have the x to the first power, x to the second, x to the third power. If our maximum power is 3, then that means that every one of these could be represented in matrix vector form, or vector matrix form. All right, so I don't need a calculator for this. So what I would do is really think of the 1, for example, and I'll just do it for the 1. 1 could be thought of as 1 plus 0x plus 0x squared plus 0x cubed. All right, because we're only concerned with the vector space related to polynomial of degree 3, that's where I would cap it. But we do know that we could expand this out to x to the nth power. All right, it's infinite. You can go as far as you want. All right, this is really all over the place now. All right, so if I had, for example, I'll just do the x cubed now. This is the same as saying 0 plus 0x plus 0x squared plus 1x cubed. All right, so this corresponds to this one, and this corresponds to that one. All right, so this is defining the basis of the vector space associated with the first derivative of a polynomial function. All right, and it's all coming from the idea that if you were to take a derivative, it's vector space related to just polynomial functions. So then what we're going to do is define what the vector space of the first derivative would look like. All right, and so I say D1 equals 0 because we're starting off with the entry 1. All right, so that's coming from, I slipped, this guy right here. The derivative of 1 is equal to 0. All right, the derivative of x is equal to 1. The derivative of x squared is equal to 2x. And the derivative of x cubed is equal to 3x squared. All right, so that defines the space related to the first derivative. All right, so now we just got to really just kind of quantify that, because this is really trying to say 0 plus 0x plus 0x squared plus 0x cubed. All right. And this one is saying 0 plus 2x plus 0x squared plus 0x cubed. And this one is saying, because the derivative is equal to 1, 0 plus 1x. I'm sorry, this one would be just a 1, right? Yeah, this is just a 1. So 1 plus 0x plus 0x squared plus 0x cubed. And then this is the square term. So 0 plus 0x plus 3x squared plus 0x cubed. All right, so that gives us the matrix for the the derivative in the appropriate order as this. So we're kind of thinking about, it's kind of weird to think of the connection to these two things, but we're thinking of this matrix is sort of along the same lines as the eigenspace of, but just related to derivatives, because we're taking in the order that we have our derivatives, going from 0 to the 1 to the 2x to the 3x squared, we're putting the vectors in that same order, all right, to correspond with the way the derivative would play out for this particular space. So I could just make a note here that through the concept or the idea of a derivative, this space is boiling down to 0, 1, 2x, 3x squared. But we don't have to worry about diagonalizing or anything like that. All we're doing is finding the image of a particular vector under that operation. All right, now this vector is coming from that polynomial function, p of t, two minus 3t plus 5t squared. So t's, x's, whatever, it's all the same because it's polynomial in nature. So we don't have a t cubed in there. Oh, we don't have a t squared is what I meant to say, because I wrote a t squared accidentally. All right, so there's the assumed 0t squared. All right, so that's where our entries come from. And so all we have to do, because anytime we perform an operation, is use matrix multiplication, right? So, formatting error. That should be on the next page. Typo bonus for somebody. All right, so what I want to do is I want to multiply this vector, which I can call P. I want to multiply in the appropriate order. I want to multiply that vector by the matrix D. So we're going to find MD multiplied by P, and that's going to be equal to P prime, all right, which would be my derivative. All right, so MD is 4 by 4, P is 4 by 1, so the result should be 4 by 1. All right, so pretty easy because there's only one pivot. Well, there should only be one pivot, but there's only one entry in each of the pivot columns. All right, so when I multiply through with a 1, with the first row, I get a -3. With the second row, clean sweep cancellation. Third row, I get a 15, and with the fourth row, I get a 0. All right. So the only thing you'd have to remember is what the structure is, and that structure is that this is in P3. All right. So this is in polynomial space order 3. All right, which is telling me that this final answer, P prime of t, should be equal to -3 plus, so we don't have a 0t, oh, well, we don't have a t term because the 0 is there, so 15t squared, all right? And it's pretty easy to see that that's what you would get if you took the first derivative of this polynomial function. The constant goes away, this would become a -3, and then power rule makes this 15t squared, all right? But it's really not getting it into this form that we're using this. It's so that we could have a strictly numerical way of evaluating a derivative. All right, so this is the basis of a lot of technology that's used for computing derivatives. Right, it converts it over by coefficients into matrix, vector matrix form, and then applies matrix operations, and then just spits out what the actual coefficients would be, and just slaps them onto the appropriate variables. All right. Now it does get a little spicier, but that's the general idea. Okay. So if you look at number 1 on the next page, which should say examples right above it, you could see an instance of where that happens. All right. So we have S is the vector space of the function spanned by the independent functions E, T, E, T, all that good stuff. We need to find the derivative of this, but what we need to do is define what the derivative matrix would look like. All right. So what I'm going to do is get to work finding the derivative of my original vector space. So e to the t, te to the t, and t squared e to the t. All right. So this is, we'll call this, well, you can call it anything you want. We'll call it f. F for function. Oh, it says s. There it is, right in front of my face. So s prime, derivative of e to the t is e to the t. This is a product rule situation. So first function, so there's a little understood multiplication there, t times the derivative of e to the t, plus the second, which is e to the t, times the derivative of the first, which is 1. So we got that. And also product rule for the third one. So first times the derivative of the second, plus the second, pen turned off, times the derivative of the first, which is 2t. Oh, poor quality squiggly bracket. There it is. All right, so I want to come up with matrices, or vectors first, then matrices that can allow me to do my differentiation. All right. So if you look at what we have in the original polynomial space, and then what we have, polynomial space, the vector space, and what we have in our derivative space, it has the same structure. So I could rewrite e to the t, I'm going to leave alone for a sec. The other one I could write as e to the t plus te to the t. And the last one, 2t e to the t plus t squared e to the t. All right. Now, this next part of the process may seem like I'm just going crazy here, but this is where our matrix is going to come into play. The matrix defined as S prime. All right. So again, this is how our space is defined by these 3 entries. So there's going to be 3 entries to our matrix. 3 entries, 3 rows to our matrix. All right. So the first one is just e to the t. So if I wrote this in vector matrix form, this one over here, we could write it as e to the t 0, 0. Well, not even. Instead of doing that, I'm just going to do what I was going to do originally. So the 3 entries will be made up by these 3 individual vectors. So if I'm looking at e to the t, I have that as part of the basis. All right, but I don't have any of these guys, which means that my first row or column is going to be 1, 0, 0, because if I'm following the structure of, and I'll do it off on the side here, where the first entry is e to the t, the second entry is some multiple of te to the t, and the last entry is some multiple of t squared e to the t. I think that's a better way to do it, because these are the 3 components. My first vector in my derivative space only has the e to the t. It doesn't have the other two terms. So it must have been a coefficient of 0 for each one of these. The second one has an e to the t and a te to the t. So I'm looking at coefficient of 1 and a 1, but it does not have a t squared e to the t. All right, so that gets a 0. Then the last one has a 2t e to the t. So it doesn't have the e to the t part of it. Right? So coefficient of 0 for that. But it does have a t e to the t term, but its coefficient is 2, so it gets a 2. And then it also has a t squared e to the t, but with a coefficient of 1. All right, so this is my derivative matrix. So any function that's defined in this way could be multiplied by this matrix in order to give its derivative. Right? And on top of that, it'll be in simplest form. That's the best part of it. Right? The thing is, it's kind of hard to justify in your mind not just taking the derivative of this. Like if I had to find a derivative of all this stuff, why not just take the derivative of this and be done with it? It's not, that's not what this is for. This is more so that you could write a program that would allow an individual user to make the program symbolically take the derivative anytime they put in something that's in this form. All right? So this is the basis of that kind of thinking, not the thinking of, I'll just have it do calculus for me. It'll replace Calc 1. That's not what this is for.
Can you explain how to get column 3?
Column 3. So we're looking at this entry here and comparing it to our basis. Right? It does not have an e to the t. So for the e to the t component, it has a coefficient of 0 because there's no e to the t in there. Right? So that's that one. Then for the t e to the t, that's present here with a coefficient of 2. So that's where that one comes from. For the t squared e to the t, it has a coefficient of 1. So that's where that comes from. All right, so we're just taking our derivatives in their simplest form and just identifying what part of the basis is there and what isn't. What isn't there gets a coefficient of 0. What is there gets whatever coefficient it has. All right, so that, it's an adjustment, but it's definitely something that can be done. So f, along the same lines, the f vector is going to come from this stuff here. So I'm just looking at the coefficients of what I have. For the e to the t term, I have a coefficient of 2. For the t e to the t term, I have a coefficient of -3. And for the t squared e to the t, I have a coefficient just of 1. Red. All right, so in order to find my derivative, f prime, all I'm going to do is multiply these two matrices together. M sub s prime multiplied by f. All right. Now it should be a pretty easy enough calculation that I think it honestly, well, from personal experience anyway, I feel like it takes more time to put it in your calculator than it does to actually do it by hand. All right, because if you take the first row and multiply it by the column of f, you're going to get a 2 and a -3. If you multiply a second row by that column, you're going to get a -3 and a 2. And then for the last one, it's just a 1. Simplify that down, you get a -1. Just making sure, -1, -1, 1. So following the same convention, we would say that our first derivative here would be -e to the t minus t e to the t plus t squared e to the t. All right, so that's what you would get if you were to take the derivative of that original function using the product rule, coefficients and everything, and then simplify it down after the fact. All right. But this is a very flexible approach because now if I have anything that's got the same structure, all I have to do is come up with a vector related to its coefficients and multiply it by that basis set of vectors, that vector space related to the derivative, and I'll be able to come up with a derivative model. All right. So programming languages are very, very flexible when it comes to numerical values, but when it comes to symbolic language, it's not always as user friendly. Right?
So that's the final answer.
So that's the final answer. And now number 2 is finding the antiderivative, which is just going in the opposite direction. All right, so what we would want to do is define our vector space related to the set of antiderivatives. So it's really just world building more than anything else. We have 1x, x squared, x cubed, dot, 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 x to the nth. Now, you might consider, well, why don't I just multiply whatever vector I get for f, by the inverse of the matrix that we had on the previous page. It's the opposite order. Problem is that matrix is not invertible, right? Because its determinant is equal to 0. So that won't work, so we need something else. So what we do is we take the antiderivative of each component, and then we define a set of basis vectors based off of that antiderivative relationship. All right. So what I want is an antiderivative vector that's flexible enough that it will produce the appropriate polynomial space. All right. So I need a matrix that produces P3, polynomial space order 3. All right. So I need this portion of it. All right, so the matrix that'll give me a capital F, because lowercase f is the derivative function of capital F of x, is going to be defined based off of the columns associated with these values. All right, so going from 1 to 3. All right, power of 1 to power of 3 is really what I'm interested in. So 1, 0, 0, 0, 1/2, 0, and 0, 0, 1/3. All right, because we're going to have the first one represent x to the first power, then x to the second, and x to the third. If you include more rows, that's not a problem. You'll just get a lot of zeros, all right? Because you'll have a lot of irrelevant values, but that's okay, all right? So, but generally what you want to do is include the ones that you need. Technically, I didn't even need the first one, all right? Because I know that the antiderivative of something to the first power is going to be to the second power. But like I said, you can't go wrong if you include too many. It's when you include too few that you have a problem. All right, so then my function f all right, we're starting off with a power of 1, so coefficient of 3. A power of 2 has a coefficient of -2. And then if there were a power of 3, it would have a coefficient of 0. All right, because it's still the same structure. Whatever the structure is of your transformation matrix, which is MF, has to be the same as the vector that defines the function itself. All right. So f of x is going to be mf as a product with f. So 3, -1, is it -1? Yeah, it's -1. Is it -1? And then 0? Oh, sorry. I'll explain this in a sec. Just butchered something. Yeah, that's the one. So, got my wires crossed there for a second. Yeah, so the function space f it's defined by its own polynomial space. So I just zigged when I should have zagged. That's x to the 0th, x to the 1st, x to the 2nd. It's mapping to polynomial space order 3. I don't know how I that mistake. But yeah, so this is defined based off of what we were learning on the previous page. Our polynomial space starts off at a power of 3, and in this case it goes to a power of 2. That's where we're starting. It's mapping into polynomial space order 3. So anyway, so when we carry out this this process, and you know, it's pretty easy to pick up on a mistake, because when you get something that's not the antiderivative of the original function, you know you screwed something up. So anyway, 0, 3/2, and -2/3. All right, so again, it's mapping into order 3, so this should now correspond with that convention, that particular convention. So 0x plus 3/2 x squared minus 2/3 x cubed, and dear Lord, I hope that's right. Yeah, it is. All right, so my capital F of x is going to be, if we simplify, 3/2 x squared minus 2/3 x cubed, which is what you would get if you applied Calc 1 concepts of basic anti-differentiation. Increase the exponent by 1, divide by the exponent. All right, little brain fart on my end. It must be that time of the hour. All right, so then I won't push my luck anymore. I was going to try to squeeze in linear regression, but I'll save that for next time. All right, so that's where we'll call it.